Welcome back. I'm glad you guys chose to come back for round two. In round one, you guys talked about what a sequence was. We learned about some of the notation with A sub n, subscripts and term numbers. We ended with sigma notation and what that means and what it looks like, a very calculus-like idea. Here for round two, we are going to talk about a more specific type of sequence this week and next week, actually. So I put two sequences up here. The first one is 15-4. I mean, you read it. You don't need to. These are two different types. The first type, we are subtracting 11 each time, or we're adding a negative 11, if you want to think of it that way, each time. And the other one, we're multiplying by 3. This one is called a geometric sequence, and we'll talk about those in greater detail next week. This is the one we're going to focus on today. We're starting at 15. We're dropping by 11 every single time. This is called an arithmetic sequence. It looks like arithmetic, spelled the exact same, but we say it differently. An arithmetic sequence, there's a difference between consecutive terms. So if you're ever just given a sequence and asked, is this arithmetic, all you have to do is subtract consecutive terms. So negative 18 minus a negative 7, that's negative 11. And then you do it again. Negative 7 minus 4, negative 11. If those differences are common, it's an arithmetic sequence. And it's easy to look at it here and say, yeah, that they're changing by the same amount each time, and they are. But they can get trickier. They can throw fractions, they can throw decimals, they can throw logs, they can throw roots. If we have this general formula, we should be able to handle that stuff. So we subtract, and we see if they're the same. If they are the same, it's an arithmetic sequence. Okay, so I tried to do this on purpose. For this sequence up here, we started at a number, and every time we moved over, we changed by the same amount. So I moved over, went down 11. Moved over, went down 11. Moved over, went down 11. That should sound a little bit familiar to us in our algebra days. And actually, I made a new one here, right? Y equals 3x plus 7. Hopefully, it sounds like a line to you guys. Y equals mx plus b. We're going to translate between the two because they are the same, right? Just like you would do in a sequence, start from this number, and how about this? Start from 7 and go up by 3 each time. That's how we would graph this thing. We'd go to our y-intercept, and we move up 3 over 1, up 3 over 1, or over 3 up 1, over 3 up 1 type of thing. That gives us y equals mx plus b. We can change this to sequence terms, right? Because a sequence follows the same sort of behavior where you start from a number and you increase it. So for us, the y would be our output. And we talked about this in the last one. The output is the actual term. M is how much we're changing by each time. Well, we just talked about this. That's the common difference, is how much you're changing by each time. Okay. X is our input. Our input is our term number. Like, do you want the 5th term? Do you want the 60th term? Whatever term number you want, N. And then B, we're getting into something here, okay? On a graph, B is the y-intercept. It's the value you get. It's the output you get when you plug in a 0 for your input, for whatever your independent variable is. So for us, we would call this a sub 0, but that's a little weird. Okay, a sub 0 is the 0th term of a sequence. What a weird thing to say, right? We have the first term of a sequence. We can have the 100th term of a sequence. But to have the 0th term of a sequence, it's a little confusing. This formula works, by the way. This formula will be fine for sequences. We can find what we need to find as long as we know that this a sub 0 is the term before the first term. We'd have to figure out whatever our pattern is. If we're subtracting by 11 each time, like we were on these ones, then the 0th term we would have to add 11 going the other way, and we'd get 26. That would be our 0th term if I was going to make a formula for this. So we can use this formula. And then in years past, sometimes I've just given this one because I think it's convenient and it's not too hard, too big of a stretch. But the problem is our book, and I know some teachers teach it, don't even give them this formula, okay? So we want to move over. Like, I don't want to do the 0th term of a sequence. I want the first term of the sequence. So if I want to scoot over one, think transformations, think translations when we did this in our pre-calculus and algebra 2 days. If we want to move over one on our sequence or on a graph, then we have to change our input, just the inside of our graph, and hopefully you're thinking of it, subtract one. Okay, if you subtract one, you're going to move over one on our sequence, and we're not talking the 0th term anymore. I moved over one, So we're actually talking the first term. Now this is the formula that we see a lot. This is what your book will give you. Both formulas are valid and say the exact same thing, but this is the one probably more popular, I guess. So to find some term of an arithmetic sequence, you need to know the common difference. How much is it changing by each time? What term number are you looking for? What location are you looking at? The 17th number, the 105th number, whatever it is. And then we need to know where to start from. Or what was the first term of your sequence? Put it all together, and then that's what we're looking at. Okay? Let's try an example here. I want you to come up with a formula. I want it to be simplified down as much as possible for this formula. If I know it's arithmetic, so it's changing by the same amount each time, I know the second term of the sequence is 1, and I know the fifth term of the sequence is 16. Why don't you hit pause and throw some effort at it, see if you can find the simplified version. It's arithmetic, so right off the bat, your final answer should look like y equals mx plus b, okay? There'll be n's and a's instead, but it will be linear in nature, okay? So we're talking that same problem a second ago. I told you the second term of the sequence is 1, so I know that n is 2, and then when the term number is 2, the entire term itself is 1. And then it said the fifth term is 16. So when the term number is 5, the entire term itself is 16. Based on that formula I gave you guys, we can just plug these in and make a system of equations. So this is a more methodical, laid out approach that will work every time. There are others, and I'll show you that other way here in a second. But there's the formula. an equals dn minus 1 plus a1. We don't know d, we don't know a1, and that's okay. That's what our equation will look like. For this one, similar. I'll plug in what I know. N is 5, an is 16, a sub n. Clean that up, and we get our second equation. So we have a system of equations. Awesome. We're experts at this by now. We're doing a lot of these. I'm going to use elimination. I'm going to subtract going down. 16 minus 1, 4d minus 1d. a1 minus a1 will be eliminated. And I'm left with a common difference of 5. I could just solve that thing and get common difference of 5. So I know it's changing by 5 each time. So I come back to my formula. A sub n. One of the things here when I ask you to write the formula, a sub n will stay a sub n. We need that in our answer. N will stay n. We need an input and we need an output as variables. Okay, it's everything else that we have to figure out. With a little back substitution, by the way, up here, if d plus a1 is 1, I could do some back substitution, solve for a1. So I get a1 is negative 4, I get d is 5. I plug those where they go in our formula. Then I just clean that up. Remember I said simplified version. You do the simplified version, and you get this. That is the sequence that has a first term that's, or second term that's 1, and fifth term that's 16. Okay? I mentioned a little shortcut, and I don't know if it's a shortcut, but there are other ways to do this. Some of you are really good with numbers. I'm sure you jumped straight here, and that's cool, but I like to think of like places, like the sequence is just a list of numbers, and I have a certain number of jumps to get from one to the other. So second term is 1, fifth term is 16. I know I have to jump 1, 2, 3 times, and in those 3 jumps I need to cover 15 spaces, right? If I'm going from 1 to 16, I need to cover 15 spaces in 3 jumps. Okay, well, just kind of using some logic there. Each jump is 5. And these jumps are the common difference. What I'm adding, add 5, add 5, add 5. So where do you solve for d? D is 5. Awesome. Okay, if I'm adding 5 each time going to the right, I could just subtract 5 going the other way. And I'm actually going to do it twice. I'm going to use that other version of the formula I gave you guys. And I want to find the 0th term. So I'm going to subtract 5 to get to negative 4. Subtract 5 again to get to negative 9. Now I can use that other version of the formula that looks like this. A sub n equals dn plus a sub 0. D is 5. We just found it right here. A sub 0 is negative 9. We just found it right here. And we're dancing. It's the same answer. 5n minus 9, 5n minus 9. The more methods we have, the more tools in your tool belt, right? Teachers, math teachers use that a lot for sure. The better equipped you are to handle whatever comes your way. Okay, so we learned about an arithmetic sequence. Right, here's a really easy one. 2, 4, 6, 8. If I add all those together, it becomes a series. So think of this as your vocab for the time being, okay? We have a sequence of numbers, and we can evaluate a series of numbers. A series of numbers is when you're going to add them together. Sequence and series. Well, good. We've been adding numbers. On our last one, we learned about the sigma notation. So it stands to reason Probably going to see some sigma notation here. Okay, before we get there, a little history lesson. There was a German mathematician, last name Gauss. And Gauss, when in his younger days, was challenged. I mean, you can embellish the story as much as you want. I've heard different versions, but his teacher was annoyed with him. He's really, really smart. He's a famous mathematician, so of course he's smart. But in his younger days, his teacher was trying to give him busy work and asked him just to add all the numbers 1 to 100. Okay, so he looked at the problem a little bit. He did a tiny bit of, analysis and gave the answer. 50-50, 5,050. And the teacher was amazed. How did you do that? And instead of just adding 1 plus 2 plus 3 plus 4 plus 5 plus 6, Gauss took a different tact with this and said, well, if I add the first number and the last number, and the second number and the second to last number, and the third number and the third to last number, you're going to get the same sum every time. In this case, 101. Okay, so the last thing to do, well, if I know there's 100 numbers, there will be 50 pairs. There will be 50 101s. Okay, well, 50 101s, did a little bit of multiplication, and got the number 50-50. Well, his process works for all arithmetic series. When adding these arithmetic sequences together, all you need to know is, what is the first one, what is the last one, and how many are there? If you know that, you can find their sum. And that's what this formula is right here. Whoa, sorry, I got caught. So S sub n is the sum of, you're adding up a certain number of numbers. N is the total number of numbers. That last one, it's actually the location of the last one, but we're going to call it the total number of numbers. A sub 1 is the first term in the sequence. A sub n is the last term of the sequence. Now, this is a little physicsy thing I'm going to do right here for you guys. We're going to make a new formula out of this. So depending on what unknowns you have, you might use the first version, you might use the second version. We already have a formula for A sub n. We just learned it a second ago. So all I'm going to do is substitute that formula we did for A sub n. I'm going to substitute it right down here and then clean up what I have. Okay, I have an A1 plus another A1 here. So that's 2 A1s. And then you could leave this like this, or you could distribute the D, whatever you want to do. But we have this alternate version. Notice, if you know how many there are, and you know the first one and the last one, like that Gauss example up there, this works awesome. If you don't know what the last one is, you could go through the process and find the last one, or you could just use this formula, because it does the same thing. How many terms there are, what's the first one, what's the common difference, and how many of them are there. We know all that stuff. So depending on your problem, you can use either one of those. Okay? Hopefully you got it written down. Moving on, and I'm going to have to get 3 videos as I'm looking at the timer. It's unfortunate, but that's okay. Got a whole week to go through these. You don't have to go watch all of them right now. So let's try, this will be the last one. We want to find the sum of, go from 1 to 5 of 2x plus 7. Hit pause, let it rip. We'll end with this one. Okay, we're back. I gave you that formula, and if you rush to that formula, you may have encountered some things that you weren't ready for, but my intention of this was to do exactly what we did on the first one. This says to plug a 1 into this, and then plug a 2, and then plug a 3, and then plug a 4, and then finally plug in a 5 into this, and then add all those numbers together. Okay, that's not too bad. That's manageable. I did that. Bam, 65. But what if I gave you the same problem? That's actually not example 2. What I want, example 2, is this one. I want you to go from 1 to 95. Now, I do not want to have to jam that many numbers into my calculator to make this happen. So we can look at this way. Because this is linear, x to the first power, or whatever variable to the first power, it's a linear function. That means it's an arithmetic sequence. And we have a formula to add up, summation, add up all the terms of an arithmetic sequence. Okay? Now try it. See if you can go back and use that formula we just did, and I'll see you guys for that last video. All right.